So we need a fast solution, and how we're going to deliver this is the answer to this problem. So if we can assume this problem as an unconstrained problem, that is neglecting the impedances and the traffic flow rates and the volumes, we're going to neglect all of those ones, and we are only interested in evacuating the people to the safer zones by only depend on the directions of these paths. So under that circumstances, we can optimize and simplify the solution. So to get this one, first we generate the graph, and then we separate the nodes. So we have the start nodes and the distribution or the destination nodes. Destination nodes are the safer zones that we need to guide the people into, and all the other nodes in the network, we can call them as the start nodes. And then the next step of the algorithm, we can group these nodes depending on some kind of criteria. The best criteria to use over here is the minimum distance criteria, where you can calculate the minimum distance by using the Dijkstra's minimum path algorithm, and you can put the weight of these links, we can assume it as all equal to 1 because it's an unconstrained problem. We are not interested in the cost function of these links. And we cannot use the Dijkstra's algorithm to develop this solution, because Dijkstra's algorithm only gives you the solution between a pair of nodes. That means you can only generate this solution for between, if you want to go from here to there, it will give you the minimum path between these two nodes, but not the rest of the nodes available over there. So you need to have a solution that is going to generate this solution from multiple nodes to multiple destination nodes. So to do that, we need to group these nodes according to the minimum distance. And before we go into that, we first need to analyze the situation where the disaster happens. When the disaster happens, some of the links of the graph may not be available, and the trap nodes might be generated as well. In this case, it gets the highest priority, and the graph will be updated and then forwarded into the algorithm. And then during the algorithm, these nodes will be grouped, and then the directions will be set from the higher order groups to the lower order groups. So this is the implementation by using the graph theory. And then the implementation of this algorithm by using the data structures and dynamic programming. I use node to represent the node information. It consists of the node information plus the link information, which is connected to the rest of the nodes. And then it constitutes the main array. And then the group, I use a stack to implement the group. Whatever the node comes in, you can push it into a particular group stack. And the last one data structure I use is the group list data structure. And the list head is the starting node who has the lowest priority over the minimum distance to the destination nodes. And then the next group can have the next higher priority, and the next higher priority goes on, so on and so forth. And these are the data structures I used. And next is the implementation of the algorithm. So the algorithm basically has three parts. In the first part, it takes a particular start node and then calculates its minimum distance by using Dijkstra's algorithm, and then put it into the group or the bucket. And then after that, it do this for all the nodes, and then after that it goes to the second part of the algorithm, where each node will be popped out from a group and then check for its links availability, and then all the links variables will be set accordingly. From higher order groups to the lower order groups, the directions will be set. And once that's been done, the algorithm will go to the third part of the algorithm, which will check for the rest of the links available. And it will take one link at a time, whatever the links available, and set all those links to 0, that to set, avoid all those paths. And also it will indicate what are the trapped nodes as well. So this is the implementation of this algorithm. And we use this algorithm, and we were very much excited about the excitation time of this algorithm. So we did the simulation for start nodes and destination nodes, and some links for the nodes as well. So we took 10, 50 and 100 start nodes, and we then took 2, 5 and 10 destination nodes, and we took about 2 to 4 links per node, 2, 3 and 4 links per node. This algorithm works really well for up to 5 start nodes and 5 destination nodes and 3 links per node. As the number of link increases, the execution time increased as well, and the algorithm needs to be further fine-tuning needed. So this is the implementation of this algorithm, and with that I will go to the applications. So this algorithm will be very useful in buildings such as hospitals and shopping malls and museums, any large buildings with complex mazes of pathways. This algorithm will be very useful. And the other one is something like a cruiser ship. We all experienced what had happened in South Korea when the ferry went down. So in such a scenario, this would be really ideal. And the other one is industrial manufacturing plants, something like power plants, nuclear power plants. And we recently experienced what happened in Fukushima when it went down. And such implementations were not there. And the other one is underground mines. When you have long and maze sort of mines, this algorithm will be very useful because it can deliver fast operations. And the last one is this can be also implemented in low population towns with less traffic or no traffic constraints. With that, I'll wind up my presentation. Thank you very much. And I think I have achieved my second task as well. All of you are.